name's John Schultz. I'm the head of computer science. I'd like to start by welcoming everyone to UCL and to the computer science department, and in particular to the inaugural lecture of Professor Tomaso Aste. So inaugurals are a grand occasion when an academic is able to give an account of a trajectory of research and development that has brought him to the highest honour of the academic profession, to become a professor. So, and it's a grand opportunity for us as a department to celebrate when our own achieve that level of success and achievement. And this year we've actually created a series of these inaugural lectures because we've had actually 6 promotions to professor, and we're very proud that 3 of those were female and 3 male. So we had actually so if you see this booklet, you'll see the dates of the other inaugurals that you were interested in. But I'd like to begin. Well, first I should apologise for not wearing a gown. I should have apologise for that. But I would like to introduce Professor Tomaso and say a little about his background and development and some of the research that he's been involved in, just to set the scene before we hand over. But so Tomaso did his undergraduate degree in the University of Geneva in physics, before going on to do a PhD at the University of Milan in material sciences. So, but at that stage he actually already ventured into the UK system. So I don't know whether that corrupted him at that point, or what brought him back to the UK later, but perhaps he spent a year at Imperial during that that PhD stage. He then did postdocs in Strasbourg and Geneva before moving to a permanent position in the Department of Applied Maths at the Australian National University, the premier university in Australia, in 2002. Where he was promoted to associate professor in 2006. It was then in 2009 that he returned to the UK and to Europe, taking a position of reader in the School of Physics at the University of Kent in Canterbury. And in 2012, we managed to persuade him to come and join the computer science department and lead our financial computing and analytics group. So we were very privileged to persuade him to make that step. And I think if I tell you a little bit about his scientific sort of trajectory, perhaps you'll understand why we were able to persuade him, and hopefully why he now calls this his home. So he started out looking at superconductivity and magnetism in matter, and then moved on to look at the emergence of organized patterns in materials, and I think made the critical observation that some of these properties that emerge are actual universal properties that are the properties of the geometry and topology of the objects, rather than the specifics necessarily of particular materials. And that enabled him to generalize that to higher dimensional systems and observe similar patterns and similar geometry emerging in that context. And this set the scene then to suddenly say, well, okay, this kind of approach doesn't just apply to physical systems, it can be applied to other phenomena, such as financial systems, biosystems, and so on. And I think that was, if you like, the entry point into the computer science world, where suddenly, data-driven problems are becoming king. And so I hope for that reason that Tomaso does feel thoroughly at home here, and we certainly are very happy to welcome him into our midst. And with that, I'll hand over now to Tomaso to deliver his overall lecture.
Thank you very much. Just, it will take forever to put this on, but I will do that otherwise. Yeah, I did it. There are plenty of space in the front here if you want to come down. Thank you very much. Thank you very much, John. Yes, I do feel at home here, and I want to say that I do feel at home here from the very first day I arrived. I felt very well and very happy to be here. And this is not usual. I mean, I've been across quite a few places, as you mentioned, and the atmosphere and the driving force here is very nice. And so I thank you for making this happen, and all the members of the department to keep this momentum on. And I hope to contribute to this myself now and in the future. Today I talk about methods to use data to construct models, to make predictions for complex systems in general and the financial system in particular. And I must confess that when I started preparing this talk some time ago, I started struggling a lot, and I didn't finish yet, but the struggle was that, as John mentioned, I've been across different disciplines, different topics, and it was not that easy to find a line that connected all these things, showing a coherent work, which is what is supposed to be done in this kind of talk. But then, actually, I found one, and it's very simple, and it is finding simple solutions to complex problems. But of course, this is not straightforward, and indeed, well, this image is often used to oppose simplicity to complexity. And clearly, if the goal is going from a point to another, from A to B, well, a straight line is the best solution. But often in science, as much as in life, the problem is not just going from A to B, and the way one takes to go is as important as the solution itself, as the end point in itself, and complexity is unavoidable. And the British philosopher said that, George Henry Lewis said that science is a systematic classification of experience. And this is a very nice example of systematic classification by a Swiss artist, Urus Weir. And you see that it's very well organized, it's quite beautiful, but however, this picture doesn't tell us much about this, the original shape, the original structure. Indeed, as Henry Louis Mencken said, he was a journalist and a philosopher himself, a scholar, said that for every complex problem there is an answer that is clear, simple, and wrong. So simple and complex, yes, finding simple solutions to complex systems is certainly, well, it is my goal, but I mean, one should be very, very careful. And by the way, both these images tell very little about this, about the system where all these things are there. And indeed, if there is a proper definition of complex system, these are systems where every detail matters, where you cannot really reduce them into parts to make sense. If you look only at the single parts, you don't catch the meaning of the system in itself. And so, what about simplicity? Where this comes from? Well, so complexity cannot be simplified into parts, but indeed, I didn't really mean simple, I mean simplex. And indeed, there has been a shape that has been characterizing all my research during the year, across the department, across the area. And these shapes have been triangles. and which are indeed called simplexes across dimensions. And what I will demonstrate to you tonight, and it's my challenge, is that how to use triangles to model complex systems and financial markets in particular, and making prediction after them. Good. Well, the idea underneath this is not new at all, and the idea is that if we can make a model that use simple geometrical properties and topological properties, then these models are likely to be universal, to be robust, and to be applicable to different many systems. And this has been probably the most persistent idea across science. This is Plato and Aristotle. Indeed, Plato proposed to associate the 5 elements to the 5 regular solids, the one that we call Platonic solids. And the same solids were used by Kepler to model, with some success, the proportion between the motions of the planets. And what about complex system? Well, in complex system, we can think that, and in general, in modeling, we can think that every idea, every concept, every piece of code, actually, every data, every piece of information, indeed, can be associated with a point in space. The space doesn't have to be the sky, it can be a complex space in either dimension. And some concepts are very well defined, some ideas very well defined, like little bright stars. Others are more confused, there is more uncertainty in others, and they are like nebulas, like cluster of galaxies. But still, you can associate points in space to every concept. And to every 2 points in space, to center of mass associated with this point, you can associate a distance. A distance doesn't have to be a metric distance, can be something a bit more complicated, but it is a measure of similarity. Closer points are more similar, distance points are less similar, and these are so similar ideas stay together, opposite ideas stay far away. And from these distances, one can build structures. One can build structure in space that connect the similar distances, and this connection between similar distances, to some extent, this connection between similar ideas, between concepts that evolve one from the other, is to some extent what we call a knowledge. And from this knowledge, from this structure, we can build the models, and I will show you that this model can be used by looking at these patterns in space. We can predict the future. We can build predictive models. Not like this exactly, but in a similar way. So a simple example about why simplexes, why triangles. Well, let me give you an example. And indeed, so we have been putting point object in space, and we are connecting them and looking at their geometry, their distance. Well, simplexes are the natural objects to use to decompose the space to some extent. And let me give an example. And the property of these simplexes, the property of these structures made with simplexes are directly associated with the property of space. Let me give an example with these equilateral triangles. And if we are on the Euclidean space, we can put 6 equilateral triangles around 1 point. And what we get something that can be repeated infinitum all around the plane. If we put less than 5, we get into structures that close on themselves. There are only elliptic spaces. And this is just by counting. It's only topology. And if we want actually to put more than 6, we can, but we have to stretch the space in 2 different directions to make more space available. And this brings us to hyperbolic geometry. And the hyperbolic geometry lives intrinsically in infinite dimension. We can put as many triangles as we wish. And so triangles are very simple shapes. Other very simple shapes are circles, are spheres, and indeed triangulation and the sphere packings are absolutely the same object from my perspective, from my geometrical kind of perspective. And in fact, in this talk, I will talk about one and the other interchangeably. And of course, doesn't have to be equal sphere, doesn't have to be perfect object, can be blurry and fluffy objects that pack in space. So, this trajectory that we saw before. Let me account briefly, and John already mentioned it actually, this what brings me here and was bringing it here from a physics background and a statistical physics background. I did graduate in physics in Genova. Then I moved to study superconductivity. Then I started looking at much more complex structures in material science environment, looking at functional materials. Then I moved to Strasbourg, looking at disordered structure, more abstract disordered structure like foams and granular materials. Then I went to Canberra, to the Australian National University, where in the Department of Applied Mathematics, where I started looking again at this packing, but in more abstract space. And in particular, I started looking at spaces that are not ordinary spaces, not Euclidean spaces, curved space, hyperbolic spaces. And when I moved to England, to Canterbury first, I am back in the physics department. I started applying this kind of structural understanding into complex system, into modeling complex system, and now I'm doing this predictive modeling for financial system. Essentially what I've been doing has been always looking, as John said, as looking at structure in space, and increasingly complex structure in increasingly complex spaces. That to some extent is the coherent pattern that I did follow. And let me go through it just to understand where these thinkings come from. So this is a superconductor levitating on a magnetic field. Although scientists are still puzzling to fully understand where the properties of this system come from, these systems are very, very simple from a structural point of view. There are a bunch of atoms, just a few, that stays in a very well-defined position, and the structure repeats identical to itself all around the space, covering entirely the space like in a never-ending wallpaper, three-dimensional wallpaper. I found instead these much more exciting. Well, the froth, the structure of froth is extremely complex. And indeed, in this structure, every bubble, every single cell is different from every other. There is no environment that repeats equal to itself all around. And nonetheless, despite the fact that these systems are intrinsically disordered, there is a good harmony, a good equilibrium, a sort of moderation. It is disordered, but it's not randomness at all. There is a lot of rules here. And in fact, this system, this structure are very complex. They are very complex in another definition of complex system, that I think is very appropriate. That is, to describe this structure, we should use a lot of information. There is a lot of information that is in this structure, and we cannot avoid to use a lot of information to describe them. And foams, froth, are the same structure as packings, and packings, we said, is the same structure of triangulation. So these are all the same kind of structure from a geometric and topological point of view. The foam is the envelope around the object that get packed, and the triangulation are the link that connect these objects. And packings are also very fascinating. They are very simple objects that get together one after the other, making very complex structures. And this is not a movie. I mean, it is a movie, but it's not a movie. This is an experiment I did in Canberra with the computer tomography, where we measured the exact position of hundreds of thousands of little spheres in a container. And interestingly enough, the previous and the only experiment of this kind that was done at that time was done here across the road by Desmond Bernal in Birkbeck. And him and his student Finney did measure, at that time was indexed by hand, about the position of a couple of thousand of spheres, and then they studied the structure of this system, etc., etc. Finney became professor here at UCL afterwards, and when I moved to England, I went, in those days he was giving his retirement lecture, so I went to see him actually at that time. And if we look at the internal structure of this sphere packing, and we look at these simplexes I was starting from those simplexes we can deduce a lot of interesting properties of this system, in particular from the network made by these simplexes. But my first work on packing was about this system. This is a system of, I make this picture, this is a system of liquid drops that grow on a flat surface, and this was used to make gas sensors actually. And there was a very complex theory about the scaling laws that follow this growth. It was, I mean, a complex theory of integral differential equation that was describing the growth. And instead I thought, no, look, I mean, should be much simple. I mean, these are just disks that grow with random point on the plane. They become as large as they can until they touch, and when they touch, they melt together and they liberate space. So it's a packing problem. And these are the kind of packing that then we went on studying, and you see they are quite beautiful, and indeed, well, at least it's my test, and indeed, actually, an Irish artist made some jewelry out of it, and I tried to get it for free, but I had to pay for it, by the way, but I have it. And the point about this packing is can be fully described just from topological point of view. And indeed, what we have three large disks that connect, that are near together. They make a triangle. Inside this triangle, there is another disk that tries to grow and make another triangle, another triangle, another triangle, one inside the other, making a fractal structure. And all the properties of the fractal structure are only related to the fact that there are triangles inside triangles inside triangles. And this is a planar graph. And by the way, this kind of graph is exactly this kind of graph that we are now using to model information in financial systems, believe it or not. And so this was about packing. Packing are very, very nice, but this is not the topic of tonight. And so what I now show you how to use this kind of geometrical reasoning to model complex systems and to model financial systems in particular. So back to this picture of information that pack in space. What we are doing, we are building this kind of network. And the point, and to some extent, this is very general. For every set of points in any kind of space, we can only associate a distance, and to this distance, we can only associate a network. Now, and the space doesn't have to be Euclidean, the point doesn't have to be punctual. We can have a volume around them, and this volume is associated with the uncertainty about the information that this point contains. Now the point is, which are the characteristics of this network? Well, the characteristics of this network are the following. The network should connect the nearest point, or at least points that are nearby, because that's exactly the point to connect similar information. Then this network should be connected. It should be connected because, as I said at the beginning, in complex systems, it is every detail matters. Every point is important. So we don't want to leave part disconnected. And then this network should be sparse. So we don't want to keep into account all the possible position, all the possible distance. We want to get a simplified picture of the system. And indeed, information in high dimension is something very difficult to represent, to understand, and to view, because the high dimension, especially non-Euclidean spaces, are very complicated spaces. And this is an opera from an artist, an American artist, Manny Lorenzo, from Florida. And however, if we simplify the system by looking at the structure of the nearby, the most similar information, then the representation is much more it can be approached, can be much more visible. And this is, for instance, the case for 100 stocks in the US market. And here, the way we build this network is by looking at the log returns, the daily log returns, and then taking the time series of this log return as the coordinates of the point in space. So we have an high-dimensional space that is as high as the length of the observation, then taking the Euclidean distance between this point and associating the distances with the Euclidean distance and the volumes in space with the volatility of the log return themselves. For the technical people here, I must stress one point here. This is not a dimensionality reduction. So we are not going down to 2 dimensions. This is a complexity reduction. We are going down to a simpler set of connection. The system stays in the original dimensional space, or if you want to do computer science tricks, we can even go to larger dimensions. That's not the point. The point is that we simplify the system of connections. And this is the same kind of construction for a bit larger number of stocks. These are 400 stocks. again in the US market. And what I want to show you now is that these networks are meaningful. They do keep information about the system. For instance, in this branch, we have all the energy production and distribution stocks, and they stay nearby to these stocks that are mining, oil industry, and energy exploration and services. On the other part of the network, we have these stocks that are semiconductors and electronics, and they stay nearby to telecommunications and computers. So the structure of this network is very meaningful. It does keep the information about the systems. And for instance, this is another example. This is the image we use for this lecture. And these are 300 stocks again on the US market. And here we have in red the one that stays more central with respect to the network, and in blue the one that stays more peripheral with respect to the network. And what we found out, what we discovered, is that the risk does not spread homogeneously inside this network. And if you invest in portfolio made of peripheral stocks, you get higher return and lower risk. And if you instead invest inside the center, you get higher risk and lower return. And this is very robust, by the way, much more robust than we thought. And it is used in these days by some firms. But of course, this construction is not static. I mean, it can be static, but of course it can be dynamic. We can follow the evolution of the risk of the market structure across time. And this is an example. And clearly the system changes. And here there is a heat map that shows the changes. So this is essentially, the red is when the system is more similar to itself, and the yellow one is less similar, and the blue is where there is almost no similarity. And these are years. You see, we start from 2001, we end up in 2012, and we see very, very clearly that around 2005, something starts to happen to the system. It starts to be less stable, less similar to itself, and then, I mean, of course, in 2007, we have the financial crisis. Nothing resembles anymore as it was before, and then little by little things start building up again, not similar to before, completely different market state, and then again actually things start to get in deteriorating. So there is a very clear dynamics and a very obvious dynamic that one can get out from these networks. And this is another example, which is here just because it's very nice, but it is about treasury interest rates. And again, I mean, each of the dots here correspond to a different treasury rate, a different maturity rates. And this is Paradigm. Paradigm is a sculpture by the British sculptor Coran de Shawcross. And it is actually it's one of the tallest piece of art in London now, and it has been just placed in front of the Crick Institute. It costed £500,000, and it is identical to our interest rate. These are the euro-dollar interest rate. And I wrote to the artist. I said, "Look, I mean, this is ours. It was 2005, you know." And actually, he was very kind. He replied me immediately. He said, "It is the unique interpretation of others, not necessarily the artistic intent, that makes the work of art really come alive." I don't know exactly what he means, but well, I suspect so. But actually, he was very, very kind, because he said he put me on his mailing list, so I'm waiting for the next vernissage. What we develop is a method, and as such can be applied to any data-rich system. And here I give you a couple of examples of other systems that are not financial. And this is an ongoing work I'm doing with a PhD student. It is about data from wearable devices. It's there. And so there are runners that participate, that monitor their own performances. And as you can see also in this case, the network, the branches of the network are significant, and we can see different branches associated with different kinds of runners, the strong, the lazy, the endurers, etc., etc. This is another work that we started, we never finished, by the way, with Henning Jensen. And these are EEG data, and this is the network associated with the data on the brain. And again, you see different parts of the map connecting and disconnecting depending on the function, and you see the dynamics of the network itself. And this is another example for a completely different system. Again, these are gene expression data, and they refer to tissue, to cancerous tissues samples. And the gene expression, we build the network from the gene expression, so the expression of protein in the different tissues. And what we see that, again, the different parts, the different branches of the network do differentiate with different cancer types. And also there are differentiation inside the cancer type. This is the diffuse large B-cell lymphoma, one quite aggressive kind of cancer in this kind of tissues. And we see we have different parts, and if we look at these different parts, we see that indeed these different parts correspond to different action of the cancer in terms of survival rates. So, I mean, there is a very good capability of description in this kind of network built from information in high dimension and connected with simplexes. But so far, what I've been showing you has been about the description and the characterization of the system. But I didn't say anything about prediction. And actually, prediction is very important. Prediction is very important. It's very important in science. It is at the center of the scientific method, which can be seen as a cyclic operation where we have observation, we have model, we have prediction, and then if the model predicts well, we can test with the observation. It doesn't predict well, we can refine the model on, and all under the principle of parsimony, where essentially we tend, although that's not always true, to keep the simpler model with respect to more complex model if they give us an equivalent level of prediction. So prediction is very, very central. And how can we map this kind of reasoning, which I think is at the center of what we should do, into our way of building these models? Well, this is our packing of information in dimension, and the observation is clearly connected with this point in space. Okay, this is clear. This is exactly what you get. You observe and you get a point in a given dimensional space. Then the volume around and also the shape of the point around is associated with uncertainty. Okay. You will never have a full information about something. The observation is limited in time. The observation is noisy. You have a volume around these points. The model is clearly the distances between this point, is the similarity measure between this point, and the connection of the network. So the network is the model. And the parsimony is the fact that the network is not fully connected. The network, we keep only part of all possible connections. And so we have all these elements, but still I'm forgetting one, which is prediction. Well, prediction is very difficult, and especially about the future. That was said by Niels Bohr. Indeed, I mean, prediction about the past is relatively similar, and is highly practiced in science. But actually, we want to predict something that has not been observed, not something that we already know. And this is very, very difficult. And in this case, for what we are doing a statistical modeling. So prediction is statistical prediction. And essentially, it means to find the probability of something to happen given the observation in the past to the moment that we are measuring. And from a statistical point of view, what we are looking is the P is therefore the probability of the system. So we have a system of variables, and we want to have what is called the joint probability distribution, the probability of everything. So once I have every variable, I want to know what is the value of each of the probability given all the set of variables. This is, unfortunately, essentially an impossible task. It is an impossible task if you have a large number of variables, as in complex systems. Here we have 300s. And because the number of parameters to estimate this grows geometrically with the dimension. And therefore, I mean, we would need an infinite number of observations to do that. But instead, at local level, to compute this local probability is not such a big deal. Actually, we have them already from the model. Indeed, the distances and the volumes of this point in space give us directly those probabilities. And those probabilities associated with the simplexes. So with the triangle, with the trihedra, and the other figures in different geometry, different spaces. So, and the network itself gives us the way to link the two. And indeed, what we have is that the joint probability is actually very simple. It's a very simple combination of the local probability of this structure of the trihedra, which is called a simple complex, and the separators. And now, once we have that, we have the way to fully model our system. And essentially, fully model our system means that from the joint probability, we can have some variables that belong to different times, so some variables that are in the before and some variables that are after, and we can find out what is the conditional probability to find something given something else. So we can make prediction. We can make prediction about the future. And so to summarize what the methodology is the following. So we observe the past, and from the observation of the past, we build this model. So we put this point in space. We generate our networks of simplexes, and which is this one. And from this network, from this structure, from the local observation, we can build the complete statistical description of the system. And then we wait a bit, we look at the future that we have not been used to build this network, and we can test whether this prediction is good or not. Of course, if we predict something with large probability and then we don't observe it, it's obvious that, I mean, the prediction was bad, so we have a low likelihood. If we predict something and this actually happens frequently, then we have a large likelihood. And so we have an instrument to tell how much our modeling, how good our modeling is to make predictions. And this is a result, this is one of the results we have. And indeed, on this axis, we have what is called the log likelihood, the likelihood that something happened. And on this x-axis, I put something I call uncertainty. It is, in this case, is 1 over the length of the data series. Of course, if you have very few data, you will have a large uncertainty. If you have a large number of data, you have little uncertainty up to, if you have an infinite number of data, in principle, for a stable system, you will have no uncertainty. And this is what I call a state-of-the-art method, which is known as the graphical lasso. It is one of the best performing methods in this system. And this is the graphical lasso for the technical audience, the graphical lasso with the same sparsity of our model. And this is our result. And we see that for a large range of uncertainty, well, here is very small time series. Here we're going below 100.4, 300 variables, so we're starting to be very high uncertainty. Our method is better. It gives better results than the graphical lasso. Well, I'm pretty sure that we can also do better here. I mean, consider that graphical lasso has about 40,000 papers so far done, and here we still not publish ours. So in the sense, I mean, there is a lot of improvement that can be done. But the point is that we can predict the future, or at least we can do it better than others. Okay, and this is very important. And the essence of this prediction is that we have been doing this in a data-driven model. And the other advantage of our method is that it's intrinsically local. So what we do is all local operation, and then we connect this local point with the network. Being local, I mean, it has technical advantages. We can do it, for instance, in parallel. There is no need to do all the local part together, but there is also other advantages that while the system changes locally, one can update the local part without bothering about the rest. So you can change parts without changing the entire system. And from a computational point of view, also from a memory point of view, this is 1,000 times faster than Lasso, by the way. Well, it depends on the size of the system, the sparsity, etc., etc. So it's very good. So we succeed to put together simple and complex, or better to say simplexes and complexes. In fact, we use simplexes as the tools for modeling, building complexes, which are called mathematical, or indeed simplical complexes, and from which we can deduct models that can predict, that can be predictive model and can predict the future. And so simple and complex together, that was the starting point of it. But actually simple and complex have something in common, something very deep in common. They always had something very deep in common. In fact, simple and complex share the same root. The words, they both come from the Proto-Indo-European root, that is twofold. You know, Proto-Indo-European language, something that we speak, but we don't know from whom it comes from. And essentially, simply means folded once. And the complex is the combination of folded several times or interconnected parts, a combination of many interconnected parts. So this is exactly what we have done. Actually, it is intrinsically in the words. Okay. That's good. Before concluding, let me thank several people that have been very important in this research, in my career in general. And let me start from the group, the Financial Computing and Analytic Group. That is a fantastic group, and it is a pleasure every morning to come to work because there is such an exciting and bright environment. And I'm not joking, actually. Then the PhD student, present and past, I think I'm not forgetting many, but I learn a lot from them. I keep learning a lot from them. I'm very grateful to them all. And many colleagues, first let me apologize to all the ones that are not there. They just disappeared. I owe a lot to them. I mean, I did a lot of nice science. I had nice time with all of them. I really enjoy intellectually, and I'm very grateful, very happy, and very lucky that I've been in contact with all these people, and many others, as I said. Then I want to give some special thanks to people that have been particularly important. The first one, I couldn't find the photograph. That's very strange, but so that's the avatar. Is Enrico Gallegani Dagliano. He was my supervisor during my master in physics. He introduced me to statistical physics and to many, many things. He's been a friend, he's been a person with whom I own a lot, intellectually and also in many other ways. Nicolas Riviere, he was my mentor at the Imperial College when I was here, then he'd been my supervisor during my postdoc in Strasbourg, and he is an amazing person, an amazing boiling mind, and he gave me a huge amount of ideas. I cannot tell you exactly how many and why, because I mean, if you know him, you understand what I'm talking about. He's bubbling out ideas every fraction of seconds. But anyway, he has been extremely influential to me. Antonio Coniglio, I owe him a lot. He taught me a lot about statistical physics, about the deep understanding of statistical physics, his deep understanding of statistical physics, and also he taught me a lot about balance between the life and the work, and that's something very important. Dennis Ware, we wrote a book together with him about packing, very successful book, and that was very useful to my career, I should say, and I would never have done it without his contribution. Stephen Hyde. Stephen Hyde was in Australia, was the head of the department in Australia when I was hired. He is a friend, he's a bright mind. He told me a lot, well, everything I know about hyperbolic spaces. He does hyperbolic geometries as fun. And I own him a lot. And Henry Jensen, who is here, actually, the only one here, that he opened his group to me when I arrived here in London, 7 years ago, and that was very important. I had very good time there in his group for about a year and with him, and so I really appreciated that very much, and I thank him a lot. And then my main co-author and my longest scientific collaboration, and also my wife. And you can imagine that the picture was this side here before, but then after several arguments it ended up here. That's not true. That's not true. Okay. Thank you very much to you all. I leave you with, before passing the scene to Philip, I leave you with some images. Some I've done myself, I collected myself, some I just collected from other sources, about simple and complex. And I think these are very beautiful pictures, I mean, my test. But the point is that it's a combination of simple element into complex shape, into complex look that make this particularly appealing. And there is harmony, there is moderation, and yet there is a lot of disorder there. I think this is really beautiful. Thank you very much.
I was hoping to go back to the picture of all the people.
Yes.
What I was reminded about this, Antonio Carluccio, the famous chef, he actually lives in our street, I'm told, but he had a very nice program on Italian wives. Before Italian wife has to get up first thing in the morning and make coffee for her husband. And then she has to get the children ready for school. And then the husband presumably comes in and drinks the coffee. And then she has to prepare the pasta for the evening. So it's only right and proper that Tiziana should be there, because obviously UCL owes you a great debt. So I think there was a wonderful presentation you made, Tomaso. I think that I'd like to say the theme about your impact on your appointment at UCL. The first thing to say is that for financial computing, we live in a golden time in London at the present. It's often quoted that within 1.5 kilometres of here, there are 3,000 fintech companies, these startup companies. So intellectually, this is a wonderful place to be. And there's a saying in English, I think it comes from the Bible actually, cometh the hour, cometh the man. And what this really means is that when you have a situation, like we have in London at the moment with financial computing, somebody steps up to do an excellent job, and this is Tomaso. Since he's been here relatively short time, he's built the financial computing group into probably the strongest research group in the department. He now has 3 MSc programs in financial risk management, computational finance, and in business analytics. And even today, this stands at 2,000 applications just for this year. So it's likely that before the end of the year, we might touch 3,000 or 4,000 applications. And what is not said is that, and where it's very important for the rest of us, this is how the computer science department is largely funded. So the financial computing group pays the bills, okay? I'm just saying this is for John's benefit. Tomaso also has an excellent collaboration with the Systemic Risk Centre, led by Jean-Pierre Zigrand, who's in the front row. And most recently, and timely, Tomaso's established the Centre for Blockchain Research, which we think, this is an interdisciplinary centre at UCL, and we think it's probably, or almost undoubtedly, the first such centre in Europe and possibly in the world. And although we think about blockchain underlying digital currencies, and this very week, two members, not of the financial computing group, but in another research group in the department, George and Sarah, have got very significant research coverage in the press for their research in RS coin with the Bank of England. So it's clearly, you know, an extremely important area. One of the areas that I think is going to be very interesting, and I hope that the Blockchain Centre will look at, is actually smart contracts. And this is likely to have an incredibly important impact on the big legal firms in London. So, you know, this is sort of research yet to happen, and puts us in a very good position. Tomaso also recruited 3 exceptional Italians, Fabio, Giacomo and Guido, and also helped Guido get an EPSRC research fellowship. And there's also the UCL coffee machine in the department, which is one of my favourites, which I'm sure you had some hand in. Interestingly, when we went to meet Anthony Finkelstein, who was the dean, he said that we convinced him that we actually were entitled to 8 additional academic staff. Right? Yes.
10, he said at the time.
Okay, but we're modest, so we agreed on 8. And when we last advertised, we had a number of really exceptional candidates, and Julius and Daniel have been appointed, and much to everybody's surprise, they weren't Italian. One has to say that trying to persuade the rest of the department that Guido is a German is not one of our greatest successes. But when we did the advert for the new lecturers, when we sent it off, the HR department objected to the inclusion of Italian nationality as an advantage. But I tried to get over that by, when we got in the applications, I suggested we sort them into 2 piles, Italians and others. But anyway, I was turned down. The other thing that I want to say is, when we look at what Tomaso's achieved in a very short time, the question is, what is he going to achieve in the next 2 years? So hopefully we might be able to turn the Centre for Blockchain Research into an institute or something such as that. But in conclusion, I'd like to finish off by pointing out to the big financial impact that the financial computing group has had, not just the intellectual, which has been covered. One of the things that you don't probably know about is that the famous UCL School of Life and Medical Sciences, SLIMS, runs a huge deficit. And the only reason it's bailed out is because of engineering. And Anthony Finkelstein, the previous dean, always used to say, I'm going to get some T-shirts printed with UCL Slims, the medical thing, supported by engineering. I then said to Anthony, why don't I get one said engineering supported by computer science? So what I did was, I thought to emphasize the impact of the computer science group, I've got a T-shirt. It's not very good, I had to make it myself. So that when Tomaso goes to negotiate for the 8 new members of staff with the provost, he'll be able to wear this T-shirt to show the impact that he's had, not just on the intellectual life, but also on the financial life. Thank you very much for running the